When trying to find a closed formula, recurrence relation, or some other type of general rule for constructing terms of a sequence, some useful things to note are there runs of the same value? Does the same value appear many times? Are terms obtained from previous terms by adding or multiplying some amount? Does the amount relate to the position in the sequence? Are the terms obtained by combining previous terms in some way? Are there cycles among terms? Does the sign switch back and forth, indicating something like a exponent power? Let's look at an example. Find a formula for the sequence 1, 1/2, 1/4, 1/8, 1/16. When we look at this, we can see that it's steadily getting smaller every time, and by a very specific amount. When we look at the denominator looks like it's 2 raising to a separate power on every iteration. So we may try a formula that looks like an is equal to 1 over 2 to the n power, with n being equal to 0, 1, 2, and so on. And as we go through and fill out the terms for that sequence, we will confirm that that does indeed work. For the next example, we have sequence 1, 3, 5, 7, and 9. And here we can see that we simply add 2 to the previous term for each item in the sequence, leaving us with an is equal to 2n plus 1, where n is equal to 0, 1, 2, ... How can we produce the terms of a sequence if the first 10 terms are 1, 3, 4, 7, 11, 18, 29, 47, 76, and 123? When we look at these, we can see this is similar to a Fibonacci sequence in that if you add the 2 previous terms, you get the sum is the next term. So 1 and 3 adds together to equal 4, and 3 and 4 will add together to equal 7. 4 and 7 will add together to equal 11. 7 and 11 will add together to equal 18. So we'll say each term is the sum of the previous 2. And we can write that as something like Ln is equal to Ln minus 1 plus Ln minus 2. And then we can say with initial conditions one, and that is L1 is equal to 1 and L2 is equal to 3. And you may note that this follows the same pattern as the Fibonacci sequence, only with different initial conditions. Sometimes a pattern is difficult to see. In these cases, it can be useful to compare the sequence to well-known sequences to see roughly where it lies in comparison to others. Next is a table with a list of common sequences and their first 10 terms. So we'll look at n squared, n cubed, n to the fourth, 2 to the n, 3 to the n factorial, and the Fibonacci sequence. And you can see all the values that are listed there. The specific terms of the values are not really what we're interested in for comparison. What we're really looking to see is, with the growth of these numbers and each one along the sequence that you're comparing to it, where does it fall? Is it roughly similar to, say, n squared or n cubed, or somewhere in between? So you're looking at just kind of where it generally lies on here. So it can be a good idea to take these sequences and sometimes graph them so you can see the growth rate of the curve on there, and then graph your sequence and see, does it fit in between a couple of these? Is it similar, or does it have just a little phase shift between them? It can be very useful to compare to these sequences. So next we'll look at an example. We'll say conjecture a formula for sequence AN if the first 10 terms of the sequence AN are 1, 7, 25, 79, 241, 727, 2185, 6559, 19681, 59,047. So if we look at that compared to the 3 to the nth power sequence, we can see that each one of the terms here is 2 less than the similarly positioned sequence in 3 to the n. So if we go and look at, say, the fourth term in the sequence, 79 in ours versus 81 in 3 to the n, again, that's consistent with our term from 3 to the n minus 2. If we go and look, say, all the way at our last term, 59,047 compared to 59,049, again, it's consistent, it's 2 less. So we can see that all that we have here is our sequence AN is equal to 3 to the n minus 2 sequence. Sorry, got to write that a little bit different. There we go. 3 to the n minus 2. And then we can say for n is greater than or equal to 1 and less than or equal to 10, and that would give us our specific sequence.